So I will talk about a project which actually is led by Houjun Mo, who is from the University of Science and Technology of China, and he is currently visiting UMass for 2 years. And here the acronym is ELUCID. Basically says exploring the local universe with reconstructed initial density field. Okay, the motivation is very, very simple. Usually we are talking about compare theory with observation in a statistical way. And of course here we are dealing with a number of problems. If your sample is not a fair sample, then you will have a cosmic variance. And basically, you could have different environments depending on where you're looking at. And also, this is related to this. In fact, in observation, perhaps we could recover some of these initial the environmental effects. But in general, maybe we have not made use of that. Now, if we can reconstruct accurately the initial condition that is responsible for the structure evolution in the local universe, then we can really just compare theory and the data in almost directly. So this project actually consists of quite a few parts, and which differentiates from similar project other groups are doing. And in fact, 2 days ago we had also a similar talk on this. So what we start with, of course, is observation, the galaxy redshift survey. And from that, we can construct, we can put galaxies in galaxy systems like clusters, groups, and maybe isolated galaxies. And here, we're using the method developed in our group, and which we call halo. This is a halo-motivated a group finder. And these groups, we are using them as a proxy of dark matter halos. And the advantage of using groups instead of galaxies themselves, that's here we can easily make corrections for redshift distortion. The reason being two, basically the nonlinear, very nonlinear evolution already occurred in dark matter halos. The realization, the finger of God is in dark matter halos. And if you exclude that on group scale or supergroup scale, and then the redshift distortion effect is really just a Kaiser effect that could be dealt with using some quasi-linear theory or something like that. And then we can make a correction for this redshift distortion and then put galaxy groups or halos, the proxy in halos, in real space. Okay? And then we can reconstruct, because the dark matter halos, they are biased tracers of dark matter. We understand actually that quite well. Then we can design some kind of smoothing process to obtain the final density field represented by the halos. And this actually is the method we developed a couple of years ago. Then you have the final density field. That is the final density field at the present day. And even from here, you can do a lot of things already. But we want to reconstruct the initial density field. And here we use, this is a Hamiltonian Markov chain method. Basically, we are not like many other methods doing. We do things backward, but here we're doing things forward. Basically, we start from some initial conditions, we assume, then we let this kind of method to search the initial conditions that match our observation the best. So once you have this reconstructed initial condition, of course, then you can do a lot of things. You can run this using n-body code or gas code, and then you can resimulate, can trace the evolution histories in the local universe. then you can have a lot of applications, which I will discuss a little bit toward the end of the talk. Okay, so this is the first part. How do we reconstruct the final density field? Here is just a plot. And as I said, you can use documented halos to trace the density field. And we use galaxy groups as a proxy. And here the red dots, they are the document or the galaxy groups were selected from this. This is a slide from SDSS. And you start from there. As I said, you make some smoothing. Unfortunately, I will not go into that. It's some kind of a tessellation or this kind of thing. And then you will get a final density field. So what I will show you, say this kind of method really works. And what basically here, the method is based on halos. So then each point in the space is assigned to a halo, okay? And according to some distance measure. That distance measure actually is a real distance scaled by the virial radius of the halo in question. So you group them according to the space into nearest labels, and then you smooth the density of these halos according to the cross correlation between halos and the mass. Okay, that's model dependent, of course. And here, this is a test. And this is the original simulated density field. And here, this is a reconstructed density field using only halos above 10 to the 12 solar mass. We don't use, if you use a smaller halos, then it will be even better. The details, we forget about anything that the galaxies that reside in halos below 10 to 12 solar mass. Okay. This is megaparsec. Well, this is just the ideal case. No redshift distortion, low group finder uncertainty, and this is what you can do, okay? Now, what you really want to test is to use mark catalogs. That is, you start from a simulation, you use some kind of way to populate your halos with galaxies, and then you include some selection function, then put things in redshift space, and then use your group finder to find the galaxy groups to represent halos. And this is how it performs. And this is the simulated, the real velocity field at, actually the simulation size. We use some smoothing. And so basically it's on something like a 2 megaparsec smoothing scale. So this is the correlation. And as you can see, this is pretty well. And here again, this is the density again on the simulated pixels. This is a pixel-pixel comparison, even you have a shift. And then the smoothness is about 3 megaparsec. Again, you see this kind of almost linear, actually this is a linear relation, this is a dotted line here. Well, so the first part actually works pretty well, and which allows, you can see this is the density divided by the mean density. This is really voids, right? This is the mean density. And here, by the way, this part, we got it correct anyway because we have halos. Well, NFW profile, but we did not plot it. This is really the outside of halos. It's already to something like 20 in terms of the density contrast. Okay. Now, this is the final density field. But if you want to reconstruct the initial density field, this is what we do. We say, this is the final density field that is you are given. Given this kind of a density field, what kind of initial conditions I require? Then this is considered of 2 parts. One is the prior parts. We assume nominal CDM model. So power spectrum. Okay. Then there's a likelihood term. Basically says, okay, I need to transform my linear density field into a modeled final density field that should match my observed density field, where is rho f. So this is the likelihood function we use. But of course, in order to do this, you need to transform the initial density field into the final density field very quickly. And this is what we use. We use a modified Zeldovich approximation, or a modified two-order Lagrangian perturbation theory. Why it is modified? Actually, this is developed by the paper here. It basically says, okay, you use an approximation, like a Zeldovich approximation, which you get one quantity. But you don't just stop there. You also use a filter, and optimal filter, to transform that into the final quantity you want. Well, this shows the performance. This is you don't have this kind of a filtering. That's what you get. And the red one is the simulated one, the real simulation, embodied simulation. And the black dots are the positions just obtained from this one. I think is the Zeldovich approximation directly. And this is a second order Lagrangian perturbation theory. And this one is with this kind of filtering. This one is also with filtering from this. You can see with filtering, this works much better. This is just simple. The detail, you can go there. So once you have this, then what you need is to probe this posterior distribution, right? And in fact, this everybody, basically you write this the likelihood function, and you take the log of it, and this can be used as something like a potential. And then you introduce the corresponding momentum, then you have a Hamiltonian here. So this is you want to find the minimum of the potential by starting from different places, from different initial conditions, different initial positions in delta, and the different velocities, right? Then in principle, you could just solve this equation and then find when you reach the bottom. So in reality, of course, what you do is that you evolve this Lagrangian system. At each step, you reduce your momentum a little bit. So cool the things down. Of course, then originally you have a large velocity, and then eventually it will cool down, and then settle into the potential minimum. Anyway, this is the detail. And here, I just demonstrate how it performs. And here, again, this is a test by true Mark catalog. True, I mean, this is the Mark catalog starting from simulations, put in, HOD, whatever, galaxies, putting in redshift space, running through the group finder, okay? So as you can see here, this is reconstructed the density field at the present time. This is our input. We got an initial condition, and then this is the original density field. From there, then we do this reconstructed present the field, and then we use this to obtain the initial condition, and then this is the final prediction of that initial condition. Okay, so this you can compare. Well, we can quantify how these things work, and here this is on small scale. And by the way, these dots here, they are halos about 10 to 12 or something like that. And then you can see again this arrangement is more or less the same. This is on small scale. They work pretty well. And you want to quantify that. This is you look at the phase correlation of your resimulated one with this original one. So that basically it is, so this one, look at the red curve. Resimulated, that's the input one, okay? And you can see this is a very large box simulation, and then at large scale, you have a perfect recovery of the phase information, and then here it will go down as you go. Well, basically you are limited by your grid size, and if you have a high resolution, again, this works better. But you cannot really do much better than this. That's because we are using 10 to 12 solar mass and the smaller scale. Okay, good. And that's great. So basically, if you read off this is k about 1 or slightly, if this is a half, and this is much smaller than your nonlinear scale. Nonlinear scale is 0.15. for this particular cosmology. Here again, now we apply this to SDSS, okay? So here this is the, basically this is the halo catalog we constructed, and then we use the halo to reconstruct the current, the present day density field, and then we use that to do the resimulation. And this is the evolution in this Great Wall region. You can see this is the Great Wall, you can see very clearly here. And so this is the final state, and this is redshift 1, redshift 2, and redshift 3. Well, there's a lot of information here. You can see some of these structures here. This is a very massive one, corresponding to here. That's already formed at redshift 2. Okay? So this is on large scale. Now you can also zoom in on Coma clusters. So this is a simulation. You can see this redshift, we could have something even earlier redshift. This is the initial condition. You can see this more or less in this filament, and then they merge together, always to here. And you can see at a redshift about 1, Coma actually is elongated in this direction. It's quite elongated. But later, this part, this filament also carries a lot of mass in. When you go to redshift about 0, this is almost round. And you can do this again and again using different realizations because your small scale is not well constrained, as I said, and see whether this large scale structure will change or not. No, it does not change that much. Okay. This is not a very good reproduction. Here, this is observation you cannot see. This is Coma, and there's a bunch of small clusters here and small. Basically, you can, trust me, they correspond to each other very well. Okay. Now, with all this, you can do a lot of things. You can look at the velocity field, right, because you have the velocity. And here, again, is the Great Wall region. You can see how these things are just going out from the void and going into the large-scale structure. And this is yet another thing. If you look at the void, this is a huge void. You look at this, and everything is just, just going away from it. The most interesting part is this one. I don't know which region. Look at this side. Okay, there's two interesting things. One thing is that if you look at this side, everything is moving in this direction because here there's probably a large-scale structure. But then if you say, I subtract the bulk motion, then you got this. Okay, and I just converge into this. But there is a very interesting thing here. Look at here, this structure here, and these arrows are pointing to. Here you don't have black dots. What are black dots? Black dots are the tracers. That is the halos above 10 to 12 solar mass. And in this region, we have galaxies. That's the white dot. But we don't have tracers. Basically, this structure here is due to large-scale compression in that region. And you do form galaxies, but then not very massive halos there. And here again, if you use, since you have the velocity field, you can, look at the tidal tensor, then you can make classifications of the galaxies where it resides. This cluster region when everything, the convergent flow in 3 directions, okay. And then filament, 2 directions, convergent flow, 1 expansion. This is a sheet. And here, there's dots in voids, blue one. You don't see them. Okay, a couple of them, okay. So this is a lot of things you can do. So this is the summary. Basically says, here, this is quite successful. And in fact, here we use only 10 to 12 solar mass halos above that. In principle, because you are constrained at a nearby region, you can use even small halos using abundance matching and assign them halos, halo mass. You can do that. Okay, so this is quite successful. And here, I think I have shown you, and even in quite detail, you can see, how the structures in the local universe evolve. I think more interestingly, with this kind of simulation, you can really do quite a lot of things, right? If you say, okay, what is the cosmic variance for a particular observation, right? If I only select galaxies from the SDSS, but I don't use all of them, or even I use all of them, maybe it's not a fair sample. But here, that allows you to control that. And you could also use, because you have the simulation, you could also use the halo merger trees for semi-analytic model that takes into account large-scale influence, right? And finally, you could also do this with gas simulation, especially like a Great Wall, these big regions. You might, have some, just SZ effect, So that eventually, I think this will provide a very good way, at least for understanding of galaxy formation and the structure formation, gas distribution, in all that actually is provided by the observations locally, like SDSS, and which you can observe in detail about the galaxy properties, or even gas properties for that matter. Okay, thank you.
I'll ask the first question. Have you studied how this depends on sort of the minimum mass halo that you
Yes, yes, yeah. We haven't done this low mass one. That's because here we use redshift, because we want to go to beyond the Great Wall. That's something like 0.09, and that actually just limit us to this kind of halo. But in fact, we are actually considering this, right? Even you don't need to have volume limited sample, right? At a larger distance, you don't have constraint for your small scale mode. But that's it. You know about that. But it will have a random mode, phase. But if you know, then at lower redshift, you do have these low mass halos or even isolated galaxies. Then you can start to see this very detailed structure, like a filament or something like that. Yeah.
Have you thought about how to sort of efficiently sort of share the sort of phase information sort of with the community at large? One thing I'm sort of sitting here and thinking of.
Well, that's the whole project. Eventually, we will release everything, and
That's why I was sort of wondering, because we have all these sort of public initial conditions generators now, sort of.
We haven't reached that point. And but eventually, what we will do is that to release all the initial conditions we generate using our method.
I think there might be efficient ways of how you could go about this.
Well, this is the thing. Yeah, this Monte Carlo, this initial condition was generated at 1024 cubed mode. That's how do you do that? It's impossible, right? The thing is that for this large-scale structure, actually, the good thing is that we are not very far from the initial condition. The constraint, the prior you have, is especially in linear theory, if you start from there, it really just go along a single line to the. So it's a one dimension in a sense. Of course, it's not a one dimension. You don't really have the complication that you have many minimums. Of course, you have minimums, but we generate from different initial starting point. They always converge more or less to the same point. So that's the good thing. I'm not saying this HMC will work for other things, but for this, it's really effective. Yeah. Oh, the Kaiser effect, that's an iterative way, because at each time we have, just the density field, and then, when we, this is basically the Zeldovich approximation kind of stuff. We use the current density field, we reconstruct it, right? And then, using the Zeldovich approximation, we know how much, what kind of velocity, what kind of the current, well, you could say initially in the Zeldovich sense. Then that's how, then if you reconstruct the density field, change a little bit, then you update your velocity field as well. There's a couple of iterations will converge. Yeah.
Can you make sure that this does not lead to fingers of God, your linear velocity field?
You don't see finger of God in our reconstruct, because as I said, the finger of God basically is all into this the halos, because we have spherical halos. And the finger of God, that actually is dealt with by our group finder. Our group finder actually is, basically, you assign a mass to a group, and that group, with that mass, you have a veil radius, the current veil radius, and then you have a velocity dispersion. Then you search in that ellipse new galaxies. You assign to it, then you update your mass, then you do again. So that basically, the clusters you select is really very elongated. That's the finger of God. Yeah.
All right. Thank you.
Okay.